Hello and welcome. In this video, we'll be diving into the fascinating world of binomial expansions, a key topic in IB mathematics analysis and approaches higher level. By the end of this session, you will be able to expand binomials using Pascal's triangle, understand and apply the binomial theorem, and solve complex problems involving coefficients and specific terms. Let's begin with a visual introduction to what a binomial expansion is. Imagine a cube with sides of length a plus b. Its total volume is simply a plus b cubed. So the volume is a plus b cubed. Now, let's subdivide this cube into 8 smaller blocks by making 3 cuts parallel to its surfaces. One cut divides the length into a and b, another divides the width, and a third divides the height. This creates a grid of 8 smaller rectangular prisms inside the larger cube. We can find the total volume by adding the volumes of these 8 individual blocks. Let's count them. We have one block with dimensions a by a, giving a volume of a cubed. There are 3 blocks with dimensions a by b, each with a volume of a squared b. Similarly, there are 3 blocks with dimensions a by b, each with a volume of ab squared. And finally, one block with dimensions b by b, giving a volume of b cubed. Adding these volumes together gives us the total volume. So the total volume is a cubed plus 3a squared b plus 3ab squared plus b cubed. Since both expressions represent the volume of the same cube, they must be equal. This gives us our first binomial expansion. A plus b cubed equals a cubed plus 3a squared b plus 3ab squared plus b cubed. This process of expanding a power of a binomial, which is an expression with 2 terms like a plus b, is what we'll be exploring in detail. Let's look at some other simple binomial expansions. We'll start with the first power. A plus b is simply a plus b. Next, the second power, which you might recognize. A plus b squared is a squared plus 2, ab plus b squared. And we've just seen the third power. A plus b cubed is a cubed plus 3a squared b plus 3ab squared plus b cubed. Now, let's investigate the patterns in these expansions. This is a crucial step in understanding the general principle. First, let's look at the powers of a and b. In the expansion of a plus b cubed, the powers of a are 3, 2, 1, and 0. The powers of b are 0, 1, 2, and 3. Notice that as we move from left to right, the power of a decreases by 1 in each term, while the power of b increases by 1. Second, let's look at the sum of the powers in each term. For a plus b cubed, the sum of the powers in every single term is 3. For a plus b squared, the sum is 2. This sum is always equal to the original power, nen. Third, let's consider the number of terms. For a plus b cubed, there are 4 terms. For a plus b squared, there are 3 terms. The number of terms is always 1 more than the power, nen. Finally, let's look at the coefficients. For a plus b cubed, the coefficients are 1, 3, 3, 1. For a plus b squared, they are 1, 2, 1. And for a plus b, they are 1, 1. These coefficients form a famous pattern known as Pascal's triangle, which we will explore next. Pascal's triangle is a triangular array of numbers, where each number is the sum of the 2 numbers directly above it. It provides the coefficients for binomial expansions. Let's build it. The top row, which we call row 0, is just the number 1. This corresponds to the expansion of a plus b, which is 1. Row 1 for a plus b has coefficients 1 and 1. Row 2 for a plus b squared has coefficients 1, 2, 1. Notice that 2 is the sum of the 2 numbers above it, 1 and 1. Row 3 for a plus b cubed has coefficients 1, 3, 3, 1. Here 3 is the sum of 1 and 2, and the other 3 is the sum of 2 and 1. This pattern continues indefinitely. To get the next row, you start and end with 1, and each inner number is the sum of the 2 numbers above it. So row 4 would be 1, 4, 6, 4, 1. And row 5 would be 1, 5, 10, 10, 5, 1. Let's use this to expand a plus b to the power of 4. We know the coefficients are 1, 4, 6, 4, 1. The powers of a start at 4 and decrease, while the powers of b start at 0 and increase. Combining these, we get a to the power of 4 plus 4a cubed b plus 6a squared b squared plus 4ab cubed plus b to the power of 4. This method is very effective for smaller powers of n. For larger powers, we'll need a more general formula, which we'll see soon. Now let's apply this knowledge to expand binomials where a and b are not just single variables. This is a common type of problem in IB exams. Let's find the expansion of 2x plus 3 cubed. We'll use the expansion for a plus b cubed that we found earlier. Remember, a plus b cubed equals a cubed plus 3a squared b plus 3a b squared plus b cubed. In our problem, a is 2x and b is 3. It's crucial to use brackets to substitute these expressions correctly. So we substitute 2x4a and 3,4b into the formula. Now we simplify each term carefully. The first term is 2x cubed, which is 2 to the power of 3 times x cubed, or 8x cubed. The second term is 3 times 2x squared times 3. That's 3 times 4x squared times 3, which is 36x squared. The third term is 3 times 2x times 3 to the power of 2. That's 3 times 2x times 9, which is 54x. And the last term is 3 to the power of 3, which is 27. So the full expansion is 8x cubed plus 36x squared plus 54x plus 27. Let's try another one, this time with a negative term. Expand x-5 cubed. Here, a is x and b is minus 5. Again, the brackets are essential. Substituting these into the formula, we get x cubed plus 3x squared minus 5 plus 3x minus 5 squared plus minus 5 cubed. Now, let's simplify. This simplifies to x cubed minus 15x squared plus 75x minus 125. Notice how the negative sign on the minus 5 causes the signs of the terms to alternate. While Pascal's triangle is great for small powers, it becomes cumbersome for larger ones. For example, expanding a plus b squared would require building 12 rows of the triangle. This is where the binomial theorem comes in. It provides a general formula for any positive integer power, nin. The theorem states that the expansion of a plus b to the power of n can be written as the sum from r equals 0 to n of the binomial coefficient, n choose r, times a to the power of n minus r, times b to the power of r. Let's break this down. The symbol to the power of n is the binomial coefficient, read as n choose r. It represents the number of ways to choose r items from a set of n items. The formula for this is n factorial divided by r factorial times n minus r factorial. The term r is the index of the term. It starts at 0 and goes up to n. It's important to note that r is the power of b in each term. This means the first term corresponds to r equals 0, the second term to r equals 1, and so on. The r plus 1 th term is given by the formula t sub r plus 1 equals to the power of n, a to the n minus r, b to the r. Let's see how this connects to Pascal's triangle. The numbers in Pascal's triangle are precisely the binomial coefficients. For example, the third row of Pascal's triangle 1, 3, 3, 1 corresponds to cubed 0, cubed 1, cubed 2, and cubed 3. This theorem is incredibly powerful because it allows us to find any term in an expansion without having to write out the entire thing. Let's put the binomial theorem into practice. We'll start with a problem that asks for specific terms. Find the seventh term of the expansion of 3x (4 / x squared) to the power of 4. First, let's identify our key values, a, b, and n. Here, a is 3x, b is minus 4/x squared, and n is 14. We need the seventh term. Remember, the general term formula is t sub r plus 1. So if we want the seventh term, r plus 1 must equal 7. This means r must be 6. Now we substitute these values into the general term formula. T sub 7 equals 14 choose 6 times 3x to the power of 14 minus 6 times minus 4/x squared to the power of 6. Let's simplify the powers. This becomes 14 choose 6 times 3x to the power of 8 times minus 4/x squared to the power of 6. Now, we apply the powers to each part of the terms in the brackets. This gives us 14 choose 6 times 3 to the power of 8 times x to the power of 8 times minus 4 to the power of 6 divided by x squared to the power of 6. Let's simplify the x terms. X squared to the power of 6 is x to the power of 12. So we have x to the power of 8 divided by x squared, which simplifies to x to the power of negative 4. The question asks for the term, so we should calculate the numerical part. 14 choose 6 is 3003. 3 to the power of 8 is 6561. Minus 4 to the power of 6 is 4096. Multiplying these together gives 80, 358, 336. Therefore, the seventh term is 80, 358, 336 times x to the power of negative 4. A very common type of problem is finding the coefficient of a specific power of x, or finding the constant term. Let's find the coefficient of x to the power of 6 and the constant term in the expansion of x squared plus 4/x squared. As always, we start with the general term. Here, a is x squared, b is 4/x, and n is 12. The general term is t sub r plus 1 equals 12 choose r times x squared to the 12 minus r times 4/x to the r. Now, we need to simplify this term, especially the powers of x. This simplifies to 12 choose r times 4 to the r times x to the power of 24 minus 3r. This is our simplified general term. Part A asks for the coefficient of x to the power of 6. This means the power of x in our general term must be 6. So we set the exponent 24 minus 3r equal to 6. Solving for r, we find that r equals 6. Now we substitute r equals 6 back into the coefficient part of our general term. The coefficient is 12 choose 6 times 4 to the 6. Calculating this gives us 3, 784, 704. Part B asks for the constant term. A constant term is one that does not contain x. This means the power of x must be 0. So, we set the exponent 24 minus 3r equal to 0. Solving for r, we find that r equals 8. Again, we substitute r equals 8 into the coefficient part of our general term. The constant term is 12 choose 8 times 4 to the 8. This calculates to 32, 440, 320. Sometimes you'll encounter problems where the binomial is part of a larger expression. Let's see how to handle that. Find the coefficient of x to the power of 5 in the expansion of x plus 3 to x1 to the power of 6. The key here is to realize that the x to the power of 5 term can be formed in two ways. We need to find the terms in the expansion of 2x1 to the power of 6 that, when multiplied by x plus 3, will result in an x to the power of 5 term. First, the x from x plus 3 can multiply an x to the power of 4 term from the binomial expansion. Second, the chakra 3 from x plus 3 can multiply an x to the power of 5 term from the binomial expansion. Let's find the general term for 2x1 to the power of 6. Here a is 2x, b is minus 1, and n is 6. The general term is 6 choose r times 2x to the 6 minus r times minus 1 to the r. Now, let's find the x to the power of 4 term. We set the power of x, which is 6r, equal to 4. This gives r equals 2. The x to the power of 4 term is 6 choose 2 times 2x to the power of 4 times minus 1 squared. This simplifies to 240x to the power of 4. Next, let's find the x to the power of 5 term. We set 6r equal to 5. This gives r equals 1. The x to the power of 5 term is 6, choose 1, times 2, x to the power of 5 times, minus 1. This simplifies to minus 192 x to the power of 5. Now we combine these with the x plus 3 part of the expression. The x to the power of 5 term is x times 240x to the power of 4, plus 3 times minus 192x to the power of 5. This gives 240x to the power of 5 minus 576x to the power of 5, which equals minus 336x to the power of 5. Therefore, the coefficient of x to the power of 5 is minus 336. Let's tackle a more advanced problem, which is a classic IB-style question. The first three terms in the expansion of 1 plus kx to the power of n are 1 minus 4x plus 15 over 2x squared. Find the values of k and n. We'll use the binomial theorem to find the first three terms in terms of k and n, and then compare them to the given terms. The general term is t sub r plus 1 equals n choose r times kx to the r. For the first term, r equals 0. T sub 1 is n choose 0 times k to the 0 times x to the 0, which simplifies to 1. This matches the given first term. For the second term, r equals 1. T sub 2 is n choose 1 times k to the 1 times x to the 1. We know n choose 1 is n, so this is nkx. For the third term, r equals 2. T sub 3 is n choose 2 times k to the 2 times x to the 2. We know n choose 2 is n times n1 over 2, so this is n1 k squared over 2 times x squared. Now we compare the coefficients of our terms with the given terms. Comparing the x terms, we get our first equation, nk equals minus 4. Comparing the x squared terms, we get our second equation, nn1 k squared over 2 equals 15 over 2. We now have a system of two equations with two variables. From equation 1, we can express k as minus 4 slash n. Substituting this into equation 2, we get nn1 times minus 4 slash n squared over 2 equals 15 over 2. Let's simplify and solve for n. This simplifies to 8n1 equals 15. Solving this gives n equals 23 over 8. Wait, I made a mistake in my calculation. Let's reevaluate. The equation is 8n1 over n equals 15 over 2. Cross-multiplying gives 16n1 equals 15n. Expanding gives 16n minus 16 equals 15n. Subtracting 15n from both sides gives n equals 16. Now that we have n, we can find k using equation 1. K equals minus 4 divided by 16, which is minus 1/4. So the values are n equals 16 and k equals minus 1/4. Let's look at another common type of problem, finding the sum of coefficients. Find the sum of the coefficients in the expansion of x cubed plus 2x squared plus 3x negative 7. This looks intimidating, but there's a very simple trick. Consider a general polynomial, p of x. If we expand p of x, we get a sum of terms, each with a coefficient and a power of x. The sum of the coefficients is a underscore n plus a underscore n1 plus a1. How can we get this sum from p of x? If we substitute x equals 1 into the polynomial, all the powers of x become 1. This leaves us with exactly the sum of the coefficients. So to find the sum of the coefficients of any polynomial, you just need to evaluate the polynomial at x equals 1. Let's apply this to our problem. Our polynomial is p of x equals x cubed plus 2x squared plus 3x negative 7. The sum of the coefficients is p1. Substituting x equals 1, we get 1 cubed plus 2 squared plus 3 7. This simplifies to 1 plus 2 plus 3 to 7, which is minus 1. Since 100 is an even number, minus 1 is 1, so the sum of the coefficients is 1. Let's look at a problem that combines the binomial theorem with the concept of roots. Expand and simplify square root 3 plus 2 to the power of 5, giving your answer in the form a plus b square root 3, where a and b are integers. We'll use the binomial theorem with a equals square root 3, b equals 2, and n equals 5. The coefficients are from row 5 of Pascal's triangle, 1, 5, 10, 10, 5, 1. The expansion is square root 3 to the power of 5 plus 5, square root 3 to the power of 4, 2 plus 10, square root 3, cubed 2, squared plus 10, square root 3, squared 2, cubed plus 5, square root 3, 2 to the power of 4 plus 2 to the power of 5. Now, let's simplify each term. Remember that square root 3 squared is 3. The first term, square root 3 to the power of 5, is square root 3 to the power of 4 times square root 3, which is 9 square root 3. The second term is 5 times square root 3 to the power of 4 times 2, which is 5 times 9 times 2, or 90. The third term is 10 times square root 3 cubed times 4, which is 10 times 3 square root 3 times 4, or 120 square root 3. The fourth term is 10 times square root 3 squared times 8, which is 10 times 3 times 8, or 240. The fifth term is 5 times square root 3 times 16, which is 80 square root 3. The last term is 2 to the power of 5, which is 32. Now we add all these simplified terms together. We group the terms with square root 3 and the integer terms. This gives us 90 plus 2, 40 plus 32, plus 9 plus 1, 20 plus 80, square root 3. The final answer is 362 plus 209 square root 3, which is in the required form. Finally, let's look at a problem that uses the binomial expansion to approximate a value. First, expand 2 plus x to the power of 6. Then, use this expansion to find the value of 2.01 to the power of 6. Part A is a standard expansion. Using the coefficients from row 6 of Pascal's triangle, 1, 6, 15, 20, 15, 6, 1, we get 2 plus x to the power of 6 equals 2 to the power of 6, plus 6, 2 to the power of 5, x plus 15, 2 to the power of 4, x squared plus 22, cubed x cubed plus 15, 2 to the power of 2, x to the power of 4, plus 6, 2, x to the power of 5 plus x to the power of 6. Simplifying the coefficients, we get 64 plus 192x plus 240x squared plus 160x cubed plus 60x to the power of 4 plus 12x to the power of 5 plus x to the power of 6. Now for part B. We want to find 2.01 to the power of 6. We can see that this is in the form 2 plus x to the power of 6 if we let x equal 0.01. So we substitute x equals 0.01 into our expansion. This gives us 64 plus 192, 0.01, plus 240, 0.01, squared plus 160, 0.01, cubed plus. Notice that the terms get very small very quickly. For a good approximation, we only need the first few terms. The first term is 64. The second is 1.92. The third is 0.024. The fourth is 0.00016. Adding these up, we get 65.94416. This is a very accurate approximation of 2.01 to the power of 6. Now it's your turn to practice. Here are 5 IB-style questions for you to try. Pause the video and work through them. Question 1. Find the coefficient of x cubed in the expansion of 2x plus 5 to the power of 6. Question 2. Find the constant term in the expansion of 3x squared plus 1 slash x to the power of 8. Question 3. The first three terms in the expansion of 1 plus kx to the power of n are 1 minus 12x plus 60x squared. find the values of k and n. Question 4. Find the coefficient of x to the power of 5 in the expansion of 2x plus 3, x2, to the power of 6. Question 5. Find the possible values of a if the coefficient of x cubed in 2x plus 1, ax squared, to the power of 9 is 288. Welcome back. Let's go through the solutions together. If you got them right, fantastic. If not, pay close attention to the steps. For question 1, the coefficient of x cubed in 2x plus 5 to the power of 6 is 2000. For question 2, the constant term in 3x squared plus 1 over x to the power of 8 is 181,440. It seems I made a mistake in creating that question. The value of r, 16 over 3, is not an integer. This means there is no constant term in that expansion. My apologies. Let's move on. For question 3, the values are n equals 15 and k equals minus 4 over 5. For question 4, the coefficient of x to the power of 5 in 2x plus 3 x power of 6 to the power of 6 is minus 192. For question 5, the possible values of a are 1 over 3 and minus 1 over 3. My apologies again for the error in question 2. I hope the other solutions were helpful. Let's quickly recap what we've learned today. We started by visualizing binomial expansion with a cube, which led us to Pascal's triangle for finding coefficients. We then introduced the powerful binomial theorem, which uses binomial coefficients to find any term in an expansion. We also saw how to apply these tools to solve various problems, including those with negative terms, multiple binomials, and unknown parameters. Mastering binomial expansions is essential for success in IBAAHL. Keep practicing these types of problems, and you'll build confidence and speed. Thank you for watching. I hope this video has been helpful. Good luck with your studies.